Okay, thank you for introduction, Rene. So, okay, work, okay. So, I will. Okay, I start. I talk about the difference of constraint patterns in used in logically constrained term-like systems. And this is joint work with Misaki Kojima and Yuto Nakamura. So I first talk about pattern completeness. So this is non-existence of undefined patterns. Pattern is a term rooted by a defined symbol, and its elements are constructor terms. Sorry, not constructor, constructor terms. And this property is usually or always checked by compilers and interpreters of programming languages. But guards are not taken into account, so ignored while running may occur. So, for example, if we consider guards when we check pattern completeness, then we need satisfiability checker for theories used in that programming languages. And some languages allow us to write user-defined function or predicate in guards, and then it's not so realistic to check full pattern completeness. So that's, but for execution of program, this is very reasonable, but okay. Then I go to the world of term rewriting. So pattern completeness is equivalent to quasi-reducibility of many-threaded term rewriting systems. And the definition is the same. So pattern, there is no undefined pattern. So all grand patterns are index of the system. And this property is usually assumed in using rewriting induction for equivalence verification, and also used to improving ground conference because the proof of ground conference uses rewriting induction. So then I talk about quasi-reducibility of rewrite systems. So let's see, this work? Okay. Let's see the example. So let's consider three sorts, nut, list, and bool, and then we consider these function symbols. So nil cons for list and zero s for nut, natural numbers, true, false for Boolean, and even is defined by the system. And then this TRS is not quasi-reducible because even is not defined for the list with length 1. And quasi-reducibility is decidable for TRSs, and the complement algorithm for left linear TRSs has been proposed, and then last year, Rene Tima and Akisa Yamada proposed a well-designed formalized algorithm for TRSs. But to the best of our knowledge, there is no result for decidability of quasi-reducibility of constraint systems. So there are some sufficient conditions for LCTRSs, but last year we transformed the Python program to LCTRSs, and then our equivalence checker failed to prove some equations because our tool has no function to check quasi-reducibility of LCTRS having some constructors, for example, list or others. So then we started to work for quasi-reducibility of LCTRS. So now this slide explains LCTRS. So, but I think everyone knows LCTRS now. So then I briefly explain. So LCTRS has sorts for theory. So in this case, we consider LCTRS with integer theory. So the theory sorts are bool and int. And theory signature includes true, false, and all integers. And theory signature includes values, this symbol, so these constants, and some operators for addition, subtraction, equality, comparison operator, logical connectives, and so on. And now we can declare user-defined symbols. So in this case, sum, and then this is LCTRS, compute summation of 0 to given number n. So sum of 3 is, so to this term, we apply the second rule, and then we obtain this term, and then we apply 3. So LCTRS includes calculation rule implicitly, and thus we can compute 3 plus minus 1, and then we obtain this term, and we apply the application of second rule, and then finally we obtain 6. So this is LCTRS. And now I explain complement algorithm for linear patterns. So complement algorithm is based on difference operator or minus over linear patterns. So S minus T returns finite set of linear patterns. So G of S denotes the set of ground constructor instances. And then, so this circle represents ground constructor instance of S, and this for T. And then you want to UN represents this red area, red, you can see. So anyway, this part is colored red. And then this operator is extended to finite sets of patterns. And then we have this property. So left linear TRS is quasi-reducible if and only if this, so difference of these two sets is empty. So the first element of operator represents all ground constructor patterns, and second element represents all ground patterns defined by the system, and then this blue part computes this the complement of, so this blue part, blue area, and this area is empty, and then there is no undefined patterns, and then system is quasi-reducible. So this is our key algorithm, and we would like to apply this technique to LCTRS, for example, equivalence verification using rewriting induction, because that technique assumes quasi-reducibility of given LCTRS. And we also working for proof system for all path reachability. And then this, so the proof system uses difference of constraint terms, and thus we would like to apply difference operator to LCTRS setting. And now I show the example. So this is our motivating example. Very artificial, but anyway, I explain. So this is the LCTRS. So over integer theory, and there are 3 thoughts, and so yeah, there are 3 rules. And my question is that, is this LCTRS quasi-reducible? Is it easy to answer? So I will show the answer, but anyway, this is our motivating question, so research question. And to answer this question, we would like to compute difference of this set and this set. So the first one is all ground patterns, and second one is defined patterns, and then we by computing difference of these patterns and check emptiness. And another question is decidability. So I would like to know this question is decidable or not. So then our goal is to have difference operator and complement algorithm for LCTRSs, and our contributions are difference operator over constraint patterns and constraint linear patterns. So after considering the extension, so sorry, when we extend the operator, so we found that left-hand side of operator do not have to be linear, and thus we can relax the condition. And then we extend complement algorithm to LCTRSs, and then finally we show decidability of quasi-reducibility of left linear LCTRS with decidable theories. And our work doesn't work for all LCTRSs. So LCTRS in this talk assumes have these two properties. So first one is that there is no non-value ground constructor term with the theory thought. That means so we can't declare user-defined constructor with theory thought. So that is very natural because in programming languages we can't declare such constructors. And we assume that non-theory signature, so user-defined part of the signature is finite. I think this is also very natural because when we write program, the number of user-defined symbols are finite. So now I explain constraint patterns. So constraint patterns is a pair of pattern and constraint. So very simple definition. So pattern has constraint, and ground constructor instance of constraint this E5 is this set. So T sigma, the set of T sigma, but sigma satisfies constraint phi. So this is very natural extension to constraint setting, and complement of constraint pattern is a set U of constraint patterns that represent complement part of this. So this is all ground constructor patterns rooted by F, and then this part is defined by this constraint term, and then this red area is complement, and you represent this red area. And for implementation, we expect finite complements. So now I explained the key operator to compute difference of patterns. So this bar operator computes complement of given constructor terms. So for example, for variable x, this returns empty set because variable x represents all ground constructor terms with thought iota. And for non-variable terms, so this case, we replace constructor by different one from left to right. So I will explain using this example. So this is example with natural numbers represented by 0 and s and then list. So then let's compute the complement of nil. And then in this case, we replace nil by cons. And there is no other symbol. And we put fresh variables. And then this is the complement of nil. And then for the second case, we replace cons by nil. And then this is one of the component. And then we keep cons. And then we put x here because x has no symbols. And then we replace nil by cons, and we put fresh variables, and then we finish the computation. And then these two are the complement of this pattern, this constructor terms. And the linearity is necessary for finite complements of patterns with infinite thoughts. If we have nonlinear term, so P of x is thought not, and then complement is this term, so P of T1 and T2, and T1 and T2 are different, and then this is infinite set, and there is no finite patterns corresponding to this set. So this linearity is very important property for this operator. And let's consider the extension. So what is difficult for extension is values. So complement operator assumes finiteness of signature and linearity of terms. But so, for example, integer LCTRS includes all integers as values. But integers are constructors in this system, and thus signature is not finite. Then let's consider complement of value 0. Then applying bar operation, then we obtain the set of non-zero integers, and this is infinite. So this is a problem for finite complement. But now we can. So we are considering constraint patterns. We have constraint. Then if term part contains value, so for example 0, then we replace 0 by fresh variable x, and we conjunct this equality, and then so we can move values to constraint part. Applying these techniques, so term part has no values. So, and then this is important proposition. So for any constraint term, there exists a value-free. So value-free means term part has no values. So value-free constraint terms representing the same grand constructor instances. But so we solved the problem of infiniteness of values, but we still assume finiteness, and thus we have this assumption. So user-defined signature is finite. And moreover, we can avoid non-linearity of logical variables. So logical variables are variables in constraint part. For example, if we have two occurrences of x in the term part, and then we can replace one of them, for example, fresh variable y, and we conjunct this equality, and then we can linearize logical variables. So then we can avoid non-linearity of logical variables. So then we can separate constructor parts and value parts. So then the extension becomes simpler. So now I explain the main result, difference operator. So, but first I briefly explain difference operator over unconstrained linear patterns. So now we assume ST of this expression has no shared variables because we have to consider unifiers, and if they have shared variables, then we can rename variables in one of them, for example, in T, then we can assume this one. And then this difference operator computes in this way. So if ST are unifiable with most general unifier sigma, then this operator returns this set. So S rho, so S sigma, that is equivalent to T sigma, is overlap part of S and T. And thus difference is this red area. And using this sigma, we compute complement part of so this part. So rho has the same domain of sigma, but they are different. And then for each variable in domain, we rho put a pattern of complement of X sigma. So I explained using example. So in this case, these are unifiable, and thus we have MGU, and then we obtain this set computing this part. So we compute complement of not near, so 0, and then we obtain S of y, and then we apply this substitution, and then we obtain this one. So this is difference operator, but linearity of S and T ensures linearity of X sigma because we compute complement of X sigma. But S does not have to be linear because of this proposition. So if T is linear, then X sigma is linear for any variable X in S. So thus we can ensure linearity of X sigma by linearity of T only. Thus we relax the linearity. So we drop linearity of S. So this is a new part, but now our main topic is extension to constraint terms. So this is the definition for unconstrained case. And then we, thanks to the first assumption on LCTRS, for every variable X appear in constraint parts, X sigma is variable, thus X rho is also variable, and then they are equivalent. And this, we have these two equivalents. So phi rho and phi sigma are equivalent, and psi rho and psi sigma are also equivalent. So this is one important property. And then we, this is another important property. So let's consider ground constructor instance of S phi. So this set can be split into two parts. S rho phi sigma. So rho computes the complement part of S sigma, and thus this is splitted. And moreover, the second part can be splitted. So one is that psi sigma doesn't hold, and then other for satisfies psi sigma, and this can be illustrated in this way. So this is overlap part. So phi and psi both constraints satisfied, and then we have two parts from the same colors. So and then this magenta and the blue parts are the difference, and that's we extend this operator in this way. So if ST are unifiable with MGU sigma and conjunction of constraint is satisfiable. So otherwise, this part is empty, and then computation is redundant, and thus we assume this is non-empty. And then in this case, so this operator returns two kinds of sets, so magenta part and blue part. So this is extension of difference operator. And then let's see the example. So let's consider these two constraint terms. So this is MGU, and then we have this rho, and thus we this constraint term, and then we have this blue part. And these two are the difference of these two. So, and then next, let's swap these constraint terms. And then this case, MGU is the same, but there is no complement substitution for MGU. So now this we swapped, and thus we have to consider variable y1, and then this is empty set, and this part is empty, and moreover, this constraint is unsatisfiable, and thus this part is empty, and then, oops, sorry, this operator returns empty set. So this is difference operator, and then I go to the extension to finite set of patterns. So this is the definition of, so this is extension to finite sets of unconstrained linear patterns. So P and Q are finite sets of linear patterns. And if S and T are unifiable, then there is some differences for overlap part, and thus we remove S from P and add S minus T, and we remove T from Q and we add T minus S, and then we recursively compute difference of two sets. This is extension to finite sets. And then extension is very simple. So we replace patterns by constraint ones. So this is original definition, and then we add constraint. That's all. But we have to show correctness of this extension, and then so there is recursive call, and then there are two sets of the recursive call, and they patterns in this sets are linear, and the recursive call is terminating, and this computes difference of two sets. So this is correctness, and then we obtain this theorem. So left linear LCTRSR is quasi-reducible if and only if this. So difference of these two sets is empty. So the first one represents all ground patterns, and second one is represents ground patterns defined by R. And thus, if this result of this computation is empty, then there is no undefined pattern, and thus R is quasi-reducible. And moreover, if LCTRS has decidable theories, then the computation of this blue part is decidable, because our definition, so difference operator checks satisfiability, and theory is decidable, and then satisfiability is decidable, and this reputation of difference, computation of difference is terminating, and then computation of this part is decidable. Then quasi-reducibility of left linear LCTRS with decidable theory is decidable. So I show, but now it's time to finish. So there is example. So we compute this difference of these two sets, and we focus on these pairs, and we obtain these two constraint patterns, and we focus these, these two, and then we obtain this one, and we focus these two, and we obtain this, and then there is no two pairs, so no pairs to compute difference, and then we obtain this set. So 8, 9, and 5, this is not empty, and thus this LCTRS is not quasi-reducible. So now I conclude my talk. So I propose the difference operator and complement algorithm for LCTRS, and show decidability of quasi-reducibility of left linear LCTRS with decidable theory. So our future work is extension of other recent algorithm to LCTRS, and we should implement our technique for implementation, and maybe extension to LCSTRS is also important future work. So that's all. Thank you for your attention.
Thank you.